I'd like to try to solve for you as an example exercise 18 in chapter 7. If you haven't read it yet, you should probably look it over and see if you can make a diagram that contains all the essential details. The problem is about a skier who coasts to rest, and you're asked to find the coefficient of kinetic friction using the work kinetic energy theorem. At first it might seem a little roundabout way, but you'll see that with a little bit of work, it's not hard to figure it out. So as I read the problem, it starts off with some skier scooting along at an initial velocity of 12 meters per second and travels a distance s, which is 184 meters, till it comes to rest on a level surface. The mass of the skier is given to be 61 kilograms. So it looks like a 2 sig fig problem, even though that's 3, that's only 2. So we'll aim for a 2 sig fig answer. So remember that the work kinetic energy theorem says that the total work done on an object has to be equal to its change in kinetic energy. And the way you make progress on these is to first ask yourself a series of questions about what things do work on the object, here the skier. And then, what's the skier's change in kinetic energy? Since we know the skier's mass and the initial and final velocity, we ought to be able to figure out what the change in kinetic energy is. So we'll have to work to figure out which things do work on the skier. So that's the first question you're going to want to ask. Which forces do work on the skier? So a quick little free body diagram would remind you that you'd have the normal force up, you'd have the weight of the skier acting downward, and if the skier were moving to the right, the frictional component of the force would be to the left. So the normal force and the weight will have to be equal, and the friction force and the normal force are related in that the friction force is the coefficient of friction times the normal. So there's our connection. So the first thing to note is that the normal force and the weight don't do any work. And the reason for that is they're perpendicular to the displacement. So the normal force is up, the displacement is sideways, the weight is down, and the displacement is sideways. So none of those do any work. And the friction force, since it's kinetic friction, is constant. So we can calculate the work done by the kinetic friction force using the force times distance formula. So the work done by the friction force is equal to the friction force times the displacement times the cosine of the angle between them. And I think you're going to see that the displacement is to the right, but the friction force is to the left. So that angle phi is 180 degrees. And because of that, this just gives us -1. So the work done by the friction force is minus the friction force times the displacement. So we got all that, and that has to be the total work because the normal force and the weight don't do any work at all. Well, we also know, using the work kinetic energy theorem, that the total work has to equal the change in kinetic energy, which is the final kinetic energy minus the initial kinetic energy. And the final kinetic energy is 0 because the final velocity is 0. So this just has to equal 1/2 mv initial squared. We end up with an equation here. Let me explain it to you. The total work, which we figured was the work done by the friction force, has to equal the change in kinetic energy, and since the final is 0, it's just -1/2 mv squared. So it looks like we can get pretty quickly to an expression that tells us what the friction force is. The minus signs cancel out, and if I just do a little bit of algebra in my head, you can pause the video and give it a try yourself. all you'd have to do is divide both sides by s and get rid of the minus sign. In any case, if you plug in the numbers here, I feel that you get 23.9 newtons. So that's the magnitude of the friction force. But the question really asked about the coefficient of friction. Well, the coefficient of friction, you have to remember, is equal to the magnitude of the friction force divided by the normal force. And the normal force is equal to the weight, which is mg. So that's going to be the friction force divided by mg. So if you plug the friction force in here, and you plug the mass in here, and use 9.81 for our friend g, I think you end up with a coefficient of friction which is 0.04, and that has no units. And by the way, 2 sig figs, those zeros are placeholders. Now there is a part B that asks a different question about a skier with a different mass. The setup is exactly the same as this, so I thought you would try part B yourself and see if you arrive at an answer that makes sense.